Design of shafts in 2 minutes. Let's go. A shaft's job is simple. Take torques from one place and deliver it to another without twisting too much, without bending too much, or failing. Step 1. Know your loads. Torques from gears or pulleys, radial forces from belts and gear mesh any axial thrust. Sketch where they sit along the shaft. Step 2. Rough size. Shear from torsion, tau approximately Tc over J bending stress, sigma approximately Mc over I quick estimate, tau approximately 16 T over Pi d cubed quick estimate, sigma approximately 32 M over Pi d cubed, pick a trial diameter so both stay under allowable stress. Step 3. Combine stresses. Bending plus torsion, often reversed over time, equivalent via von Mises, or maximum shear theory. Apply a safety factor if fatigue matters. SN data, surface finish, size effects, and stress concentrations. Step 4. Watch the hot spots. Keyways, shoulders, snap ring grooves. Those notch the shaft at generous fillets. Avoid sharp transition splines, and interference fits to reduce Kate. Step 5. Stiffness and alignment. Limit twist. Theta approximately TL over GJ, keep deflection small so gears mesh cleanly, and seals, don't leak check bearing spans, and add supports, if needed. Step 6. Vibration. Estimate critical speed from mass and support stiffness, operate well below critical speed or design to pass through quickly. Materials and finish. Medium carbon steels are workhorses alloy steels for higher strength hollow shafts, if weight matters better surface finish, and case hardening boost fatigue life. Final pass. Verify stresses, verify fatigue, verify deflection, verify critical speed lock and tolerances, lock and fits, lock and keyway details per standards. That's the blueprint. Define loads, size, combine, de-notch, stiffen, de-vibe, finalize, build smart.